get started. Today, we are going to talk about transformers. So the main paper that we are going to talk about is a paper titled Attention is All You Need. I believe it was published or it was released in 2017. The last time I checked, this paper had more than 100K citations. This kind of shows the importance of the transformers in modern AI and machine learning models. All right, so instead of just going through the different elements and different blocks in the transformers, what I want us to do is to develop and design a transformer ourselves, right? Together, we want to think, why do we need a particular process? Why do we need a particular block? What are the choices that we can have? And hopefully we can learn a little bit more, and perhaps we can have some ideas about improving the transformer architectures or coming up with new architectures. All right. We are going to focus on an NLP application, which is translation. But transformers have been used in a variety of different domains and applications. In fact, perhaps end of today's lecture or next lecture, I'll talk about vision transformers. Basically, a similar architecture applied to image domains and vision applications. All right. So what is the problem that we are interested in solving? Let's say I have a phrase in Spanish. I did Google Translate, so I'm not sure how accurate it is, but let's say me encanta UMD. All right, and we want to develop a method based on transformers to translate this. And the translation to English is I love UMD. All right. So what is the overall architecture? So the overall architecture is an encoder-decoder architecture. So you get an input. And so here's my overall architecture. As your input, you get your original text, original sentence, me encanta UMD. Original phrase. And as the output, I want to generate the translated version, which is I love UMD. All right. So first, this text or a form of this text that we will talk about will go through a part of the model called encoder. So what is the job of the encoder? The job of the encoder is to encode information for each word or token, another way of saying a word, based on the context of that phrase. So for each word or token here, the output of the encoder is going to be a vector. So I have 3 words, so I'm going to have 3 vectors here with a particular length. That is my design choice. Okay. So probably you are familiar with word embedding, right? So you can embed word or a token to a vector. So if I do that, okay, so I'm going to get an embedding for the first word, I'm going to get an embedding for the second word, I'm going to get an embedding for the third word. Okay, fantastic, right? So I have my vectors, then I should be done. But the issue is that obviously we want to have the context information, even encoded in the each token's embedding. So we don't want the embedding to be context agnostic. So we want the context information to also be present in each of the vectors. So that is why we need some sort of dependencies across these paths. So that's something that we are going to think about. Okay. So this is the encoder part. Now I get vectors somehow for each token that combines the information, not only for that token, but also for other tokens. Then I'm going to have a decoder. So this is my decoder. So this information is going to be transmitted to the decoder. Again, we are going to explain how that works. And I want to be able to decode, meaning that in this application to be able to translate. So in my decoder, I don't have any input. Right? So I'll start with like some generic token, which is called the start token or start of the sentence, SOS token. So here we have the start token. And I will generate my first output word from my decoder. In that case, it will be the word I. And then I will use the generated word I as the input for the next step in the decoder. Okay, so I say I generated this token I. Then for the next time, so this is step 1. For step 2 in my decoding, not only I'm going to have the start token as an input to my decoder, I'm going to have the previously generated token, which is I, to my decoder and generate the next word. In this case, it will be love and keep going. So that is going to be my decoding process. Remember, in the different decoding steps, the encoder is fixed, right? So you've already encoded the information, you're good, right? So you're done. Then you're basically repeatedly decoding the next word, right? So you start with the start token. Say, based on the information I have, start token, what would be the most likely or most appropriate first word as my output? You generate that, you have that as your input, then you can say, okay, so I have the start token, I have the word I, what would be, and based on like the encoded information of my original phrase, what would be the most appropriate selection for my next word and my next token? And you keep going. When do we stop? We stop when we generate the end of the sentence token. Decoding stops when end of the sentence token is generated. And that's it. So that is the way that transformers work in a high level from an application point of view. So as you can see, every step of the decoder depends on the previously generated tokens. So that is why these models are also referred to as autoregressive models. Right, I think there's a question, yes?
Does it rely on all previously generated tokens or just a single previous token?
All previously generated tokens. All right, so that is encoding and decoding in a high level. Right? Now, our main focus in today's lecture is, first of all, how can we encode information in a context into vectors? Second of all, how can we transmit that information to the decoder side? And third of all, how can we use that information in an autoregressive fashion to be able to decode that information and generate the output tokens? So that's basically the three parts that we want to learn today. Okay. So let's start with the encoder side. Okay. Right, so here's my encoder. These are the words that I had, me and Kanta, UMD. Okay, so probably, we can't have words as input to the model, right? So we need to translate the words to real vectors because all of these models, they work with real vectors. Okay. So what is the process to translate words into real vectors? Embedding, like we'll embed these words into a space, high dimensional space. Usually we have vectors with 512, the length 512, as the word embeddings. So that's the first step. But as I mentioned, the output of the encoder is going to also be a vector of length, let's say the same length, 512, for each token. Maybe I already answered, but why do we need to design an encoder? So why can't we use word embeddings itself? The context, right? So it is really important to not lose that information because one word may have like different meanings. Also, we want to be able to encode the meaning of a sentence into these vectors, and you'll see how those vectors can be used, right? All right.
Would the output be similar to the embedding?
Good question. So we'll have to see. I hope not, right? Because you need to have like some sort of context information embedded in these output vectors. But we need to think about it, to have an architecture, not to spit out vectors that are extremely similar to your original word embedding. In that case, what are we doing? Good. All right. Suppose we have, I tell you, okay, there is a good architecture as my encoder. It takes input tokens, x1, x2, x3. These are the notations we are going to use. It spits out z1, z2, z3. Okay. What if I change the positions of these words, of these tokens? So do you expect if I change the positions, let's say for this example, I have x2 first, and then x1, and then x3. So do you expect to get z2, z1, z3 as the outputs, or do you think it should be some other vectors that is different than the previously encoded versions of these tokens? Okay, so it should change, right? So if you're changing the order, you're changing the context. Maybe the phrase is no longer meaningful, right? Or sometimes when you are permuting the tokens, maybe the meaning of the sentence is completely different. Therefore, your embeddings should have different meanings. But the architectures that we have, they don't have this property, right? So they don't have the understanding of the position of the tokens. So the tokens is like, okay, so you have like these inputs, similar to like what you have in feed-forward networks, right? So you can permute the inputs, the order really doesn't matter. This is in contrast with other recurrent neural networks like LSTMs, where there is an intrinsic order to the inputs to your model. You know, okay, here's time one or token one, time two, token two, towards them. So transformers is not like that. So how can we solve this problem? What would be an idea? Because the architecture itself doesn't incorporate intrinsically the order of the tokens. So we need to somehow manage it in a different way. So how can we deal with this problem? Okay, good. So the idea is quite simple. The idea is to add some vectors unique to each position to the embeddings of the token in that particular position. And so what I mean is the following. So instead of having x1, x2, and x3 as my word embeddings as an input to the transformer, I'm going to have a positional embedding 1 for position 1, another vector positional embedding 2 for position 2, and positional embedding 3. What is the length of these vectors? It is the same length, 512. I'm just going to add them with my original x1 and x2 and have that as the input to my encoder. So can I have, hold on one second. Can I have a positional encoding vector in a way that this vector for position 1 and the vector for position 3, they're the same? Or for position 1 and position 20, they're the same. We can have it, right? Because you want the information about the position to be corresponding to that vector. There should be a one-to-one correspondence. But with that constraint, you can use like whatever, basically whatever you want, right? So you can use different functions to generate these vectors. The only constraint here is that you don't want to have collision. You don't want to have like two, positional embeddings to be the same with in different positions. Okay? So in the paper, they originally used this particular function for a particular position for the even coordinates, like let's say coordinate 2. They use a sine function, the position divided by, let's say 10,000 to the power 2i over the size of the embeddings, which is 512. And for the even, for the odd positions, it is basically the same, but the cosine function. But effectively, you can use different positional encoding functions. There is nothing unique about it. There have been many different proposals in the last couple of years, but this one also works. So that's why it was used in the original paper. Okay, so the input to the encoder, therefore, is the embedding of a word plus positional encoding vector corresponding to that particular position. You sum it up, you have it as an input to that encoder. Okay, so there were a couple of questions. There was a question. Yes?
Yes. So when you say the original word has the positional encoding added to it, is that like an arithmetic addition or is that concatenation?
No, just adding, arithmetic. Just add like two vectors and you'll get one vector. You don't concatenate. Yes?
Is the absolute positional encoding actually necessary, or it's only we can do with relative positions of one word with respect to the other? Because if the input vector changes, then we again need to do the thing again.
I don't think it is necessary. I'm sure that if you come up with a smart relative encoding vector for positions, that should work. But I don't have it on top of my head to point you to a particular reference. Maybe one more question, because I have a few pages of notes. Yeah, you go ahead.
How do you know that add just simple addition can embed positional information into the?
So what we know is that these vectors, these position vectors, are unique to that position. So if I see that particular vector itself, I know, okay, so this vector corresponds to position 121. That's what I know. But what I don't know is that if I'm adding it to my embedding and I'm pushing it through whatever we are going to cover here, it actually encodes the position in the final embedding of that word. We'll have to see how that happens. Short answer is that empirically, it seems to be an effective way of handling. Okay, let me continue, and I'll come back to your questions later. Okay. So far we learned what is the input to an encoder. But there is no, before even going into what is happening, okay, I'm scaring you off about what is happening inside of the encoder. But before even going through what is happening inside of an encoder, maybe I can even think about this problem in a system level. Right? Suppose you have an encoder. An encoder. What is the input? The first input is vectors. The embeddings, word embeddings plus positional embeddings for each token, 512, the length. So what is the output? As I mentioned, the output has the same length. So one vector per token. Okay. Can I add another encoder on top of it? Yeah, because the same length, right, in terms of the vectors. Now I can add another encoder on top of it. And I will get the outputs as, again, 512 vectors. How many encoders I can have on top of each other? The sky is the limit, right? But in the original transformer, they stacked up 6 encoders on top of each other. I'm assuming that they tried with 4 and 5 and they saw an improvement, and they tried 6, they saw an improvement, maybe they tried 7 and maybe the improvement wasn't great and they stopped, right? So there is probably nothing magical about the number 6, probably. Okay, so that is the idea of stacking up the encoders. As I mentioned in the original, oh, stop the. Okay, we still have one of them, right? So hopefully you can see. 6 encoders. I think probably this one is restarting. It may take a couple of minutes. All right. All right, let's now look at the scary part. So what is a function? What is this function? What is a function to take 3 vectors and spits out 3 vectors with the same length? So let's design that function together. A look inside the encoder. right? So my goal is to design a function. I have 3 vectors, each with a length of 512, and it spits out another 3 vectors, each with a length of 512. All right, so what would be a good candidate for such a function? So let's think together, right? So what is the simplest neural network we know? I covered it in the previous lecture. Fully connected neural networks, right? So let's see if we can use a fully connected neural network, because that is the simplest choice for us. Right? Okay, so if I concatenate these inputs and apply fully connected neural networks, then it is a little bit messy, right? Because then the outputs may, be just one vector, then I need to chop it off to like different chunks. It is complicated. But perhaps I can take a fully connected network and I apply on each vector individually. So what I mean by that is, again, suppose x1, x2, x3. You take x1, it is a vector of 512 numbers. You apply a fully connected network to it. And you generate another 512 numbers as your output. So you took this network, you applied it to the first vector, you get your first output. Okay, so it's the problem when you use fancy, notepads. Okay. All right. So here we have a fully connected feed-forward network. Feed-forward network. You get this, but you apply the same network, but on X2. Feed-forward network, same weights. Get the output for the second one. Feed forward network, and you get the Z3. Right? As you can see, writing 3 blocks of feed forward network is not easy. So from now on, I'm going to show this like this. Feed forward network with an understanding that this is applied to each of the vectors and you generate the output for that particular vector. In other words, it is applied pointwise. Okay, are we good? No, we have a neural network. It takes your input vectors, it outputs output vectors. A little bit fancier than embedding. So are we done? Did we design a good quote unquote transformer? If not, what is the issue? Yeah, again, right? You're taking an embedding and you're just massaging that embedding. You're spitting out another embedding. There's no like context information, right? So that's the whole point. So we need to somehow incorporate the context information. Encode the context information. All right. And that is where an attention layer comes into the picture. Attention layer is to encode context information in our encoder. So here's how it looks like. So you have, again, x1, x2, x3. I'll first pass them through an attention layer or self-attention layer. So the output of the self-attention layer will be again 3 vectors with a length of 512. Right? So these are 3 vectors. But since I already talked about feed-forward network, and usually it won't hurt to add a little bit complexity to our transformations, let's add a feed-forward network on top of it. I understand it is not bringing context information, but it can massage each embedding perhaps to highlight more relevant information in the output embeddings. So hopefully it won't hurt. So we'll add a feed-forward network on top of it. And the output will be 3 vectors with 512 lengths. So there is a intrinsically big difference between these 2 blocks, right? Even though I'm drawing them in the same way. So the feed forward, this one, is applied pointwise to each vector. There's no cross-talking between the tokens. While the self-attention is the only place where the different vector informations, they get somehow smashed together, and there's a cross-dependency across them. All right. But one really advantage of, so as I mentioned, this is applied to each vector separately. But one advantage of this is that this part can be done in parallel. So I have a feed-forward network. It needs to be applied to each token, each of these vectors separately. I can do it in parallel. I don't need to wait for other results to be able to perform that individual operation. This is really the essence of seeing some really improvement in terms of the training time and parallelization for the transformer. So this is the part. So this part can be done in parallel. And in fact, in the original paper, compared to the other recurrent neural networks, having faster training is one advantage of transformers. Okay, so and that's the key in getting that information. So next, I'll talk about the self-attention. So basically, we came to this point that we have a good design for the encoder already. If I give you a good design for self-attention, we are done, right? So because you can stack up the encoders, we are done with the encoder side. Now we need to think how we can use context information for the self-attention design. So that's going to be the next part. There was a question. Let me pause. You had a question? Oh, already answered. Okay, good. All right, so the next part is self-attention layer. Okay. So I'm going to only focus on this part because the rest we know how to do it. And for simplicity, even though I was calling the output vector Z1, Z2, Z3, for the self-attention, I'm also going to call the output Z1, Z2, Z3. I've used of notation because I like Z notation as my output, but you figure it out. Okay. So how about this design? I'll give you a choice. We'll see if you like it or not. How about that? How about this design? So I have three vectors as my input, x1, x2, x3. And I want to get z1, z2, z3. Okay, so the way I'm going to do is I'm going to compute the z's as a vector product. I'm going to multiply x1 with a matrix. Let's call WB, z2 as a matrix multiplication of x2 with the same matrix, and z3 x3 times WB. Would this work? Again, no, why not? There is no crosstalk. Thank you, thank you. No crosstalk. I don't like this. Okay. All right, so how can I make these equations to depend on one another? So then let's not call them z's. Let's call them, because I'm multiplying with WV, let's call them vectors v1, v2, and v3. All right, so what if I tell you that maybe word 1, x1, and x2, they are very important to each other. So I need some information about embedding of x2 to be encoded in the embedding of x1. Obviously, the embedding of x1 by itself is important, its own embedding. But embedding of x3, I don't know, like maybe we don't need to have them talk. I don't need any information about embedding of x3 in embedding of x1. So in other words, what if I give you the following matrix, a matrix P that has 3 rows, x1, x, and 3 columns, and it has probabilities how much of that embedding of that particular token I want to be included in the final embeddings of that particular token. So let's say for the final embedding, let's focus on row 1. This will be used for the final embedding of the first token. Obviously, the embedding of x1 itself is going to be important. Let's give a weight of, let's say, 0.8 to it. Embedding of maybe word x2 is relatively important, 0.2, but for this particular token, I really don't care about the third token, the third embedding, 0. Right, so as you can see, this is a probability vector because normalization is easier, right? So you could have done it with like other numbers, but better to normalize it to sum it, to have it sum to 1. It's another normalization. Okay, same for output embedding of x2. I would say x1 is maybe important, but not as much as the one that x2 was important to x1. x2 for itself is obviously important, but here x3 is important for x. And let's do one more. Let's do with green. Right, so I get, for example, this particular matrix, 0.4. So this P is my attention matrix. Suppose I'm giving it to you for now. Right, then the output, my output would be Z1 would be 0.8 times X1, or I can use a linear transform version of X1. But maybe that gives me a little bit more flexibility, the way that I'm massaging each embedding. Right? So again, remember, X1 to V1 is like another pointwise transformation, like the one that we did for feed forward. So it really doesn't hurt. All right, so instead of adding x1, I'm going to use v1. So I'm going to say my output will be 0.8 times v1 plus 0.2 times v2 plus 0 times v3. For my second output, it's going to be 0.1 times v1 plus 0.7 times v2 plus 0.2 times v3. And for the third one, we have 0.3 times v1, 0.3 times v2 plus 0.4 times v4. So as you can see, this can be written in a matrix form. It is easier. Think about a matrix of z's with the rows z1, z2, z3. It's a matrix of z. I can write this as matrix P, the attention matrix, times the matrix of v's. The rows are v1s, v2, and v3. So that's it. My learnable parameters would be what? Learnable. Obviously, WB, the matrix that we are using for transforming each embedding to the V vector, plus the attention matrix, right? So these are the maybe like each parameter, each element of the attention matrix. I'll learn in my optimization. If I do that, then I can use P times the V1s, V2s, V3s. I'll get the output Z's, and that's it. Right? So I'll have an attention layer with parameters WV and P. Done. Questions? Yes.
I didn't understand why you do WB.
You don't have to, but it doesn't hurt to maybe add another linear transformation on top of x's, especially if you want to work in a different dimensions than the original 512 dimension, because you can perhaps have dimensions of these a little bit smaller. In fact, in practice, the V's are in the original design, they have lengths of 64 compared to the original 512. But there is no fundamental reason of adding for now.
So WB is not a square matrix, right?
So which matrix?
It's not a square matrix. It's
No, it doesn't have to be a square matrix.
not just any condition.
Not yet. Free like a bird. One more question? Yes?
Just clarifying, you're talking about WB, right?
Yes. Yes?
How does someone go about constructing an attention matrix?
Good question. Right? We'll talk about that. Okay, so for now, I'm somehow asking my optimization, in fact, answering to your question, my optimization to learn not only like this WV matrix, which is okay, just massaging the individual embeddings, as well as the attention matrix P itself. But do you see any issues? Any issues about this? Maybe constrained. Okay, fine. The row sums are 1. Not a huge deal. Any other issues? Not necessarily, right? Because you have P and you have like V's that are functions of WV. So you have a product of the two. So it is non-linear. So that's not the issue.
P should be full rank.
Forget about it is not like full rank because the row sum should be 1, but I don't like have any other constraints. Like someone from the back, sorry, so the last row, someone from the I won't let you guys sleep. How about that? Okay, so you can't because you're the row like right in front of the last row. Okay, go ahead. Yeah. Okay, but like I already, hopefully handled the responses that maybe like the word ordering and stuff may may be different if you shuffle it, but I already handled it, in my input as by adding like the positional encoding vectors.
Is it because this complexity of the P matrix pertains to it was
What is n?
the number of embeddings we have?
Okay, good. Okay, I like it. So let's look at the dimensionality of P. So I kind of, hid it because my example is like so small, right? So three tokens, but P is an n by n matrix. What is n? N is the number of input tokens. Just imagine that you are handling maybe 10,000 words. That's not even like, huge. Then P, if your n is like 10,000, then P has like 10 to the 8, 10,000 squared, roughly speaking, parameters. So that is one issue to learn such a matrix. Is learning even possible? Because you want something that is common across different training examples, right? As your attention, you want to learn something intrinsic about your trainings, but P here is going to be like this huge matrix, perhaps very specific to each particular training with a lot of parameters, and perhaps more importantly, it is variable length. Maybe you can set a maximum length like 10,000, have other entries as zeros, but you can see like that can be a big headache for your implementation. Okay, not good. So what is the idea? The idea to solve this problem is quite simple. The idea is to have a particular structure in your matrix P in a way that can be learned quite easily. All right, so we are going to use two intermediate matrices, WK and WQ. K, roughly speaking, refers to keys, and Q for queries. But these are just matrices. So what I'm going to do is the following. I'm going to multiply x1 with WQ. I'll get a vector Q1. I'll multiply x1 with my key matrix, WK, get K1. For x2, I'll do the same thing, multiply with WK matrix, get K2. And for this example, I have 3 tokens. I'll do the same thing for the third one. So basically, I multiply WQ and WK to all x's. I'll get their Q vectors and their K vectors. Easy multiplication. And then to compute my P, I'm going to look at the similarities between the query for the first embedding, the Q1 with K1, K2, and K3. Depending on the similarities, I'll convert these similarities to probabilities. That's it. That will be my P matrix. So what is your favorite similarity measure between two vectors? Cosine similarity is inner product, right? So suppose I multiply Q1 to K1, I get like a value 10. I multiply Q1 to K2, I get a value of 5. I multiply Q1 to K3, I get a value of 2. I want to convert these numbers to probabilities. So what is the function that we usually use? Softmax, right? Softmax, you have like 3 numbers, it converts it to probabilities. So apply a softmax. Softmax. Then you will get 3 probabilities. Okay, I really don't know what would be the softmax value, but I would say, okay, just for consistency, okay, I can get 0 for the last one. I'll say 0.75, 0.2, and 0.05. This will be the first row in my matrix P. That's how I constructed the attention probabilities. With a really minor technical caveat. So in the paper, what they suggest is that we don't push these numbers to the softmax, we divide them by the square root of the dimension of the key vector. And I think this is an empirical observation, but they have argued that this helps the speed of the training. That's just empirical. So you take these similarities. Now you can think about your similarity as like, you know, the inner product divided by the square root of the dimensions, push it to the softmax, you get the probability vectors. So as I mentioned, this will be the first row of your P matrix. So for the second row, what do? You look at Q2. Again, you look at the similarities between K1, K2, and K3. Get the numbers, normalize, push it through the softmax. And you do the same thing for the third row. So from a matrix point of view, so what you're doing is you multiply your X, which is a vector, a matrix whose vectors are X1, X2, and X3, with a matrix WQ, you get the Q. You multiply X with a matrix WK, you get K. And your P matrix, your attention matrix, is nothing but softmax of Q K transpose, that's the inner product, divided by the dimensionality of your key. That is your P matrix. And you use that in your attention layer. So here, the learnable parameters obviously are your Curie matrix, your key matrix. And before, remember, we had the WV, which is called the value matrix. All right. Now let's count how many parameters do I need for computing P. Does it depend on the number of tokens? So I have WK. It's a matrix applied to X1, X2, and X3 to get the Curies. So this is a matrix, let's say, from 512 to another 512, or let's say 64. But the same matrix is applied to different X's, right? So it really doesn't depend on N, the number of tokens you have. Same for the other matrix, WQ. Therefore, we basically got rid of the dependence on the number of tokens in our attention matrix. No dependence on n, which is the number of tokens. Okay, so let me pause, see if there are any questions. Scroll down. Questions? Yes.
Before you were using W small q, and now you're using W big Q. Are there other
W small q. Oh, you are right, my friend. This was a test to see who is sleeping and who is not. You are not sleeping. Good. Oh, fantastic. Good. You'll get an A+. Okay. All right. So I hope we are done. Are we done? Mehtad, yes.
So why did they actually do this? Because it doesn't have the number of parameters.
It is essential to not have P as the number of parameters as the number of tokens. Because not only just like you may also deal with smaller sentences, but the cross-learning across different input samples will be extremely difficult in that case. So here, what you're learning is these intrinsic matrices, WQ, WK, and these are potentially have better generalization across different samples. So that's another idea.
So if we don't care about the complexity of tokens, if we have a limit on the number of tokens, just learning the P
is still perhaps if you could converge, but I would say your convergence might have some issues in terms of generalization. So let me push through because we have about 15 minutes. So I want to be in a good position for the next lecture. Okay, are we done? So we are already good, right? Because we have developed this self-attention. The tokens talk to each other, fantastic. Feed-forward network after that, and that's the encoder. But what if, I'm not saying this happens, what if you do all of this and you get a matrix, self-attention matrix, something like this, right? So you get a really big value here, you get almost 0 here, 0 here, another big value here, 0 here, 0 here, another big value here. By 0, I mean let's say 0.1, something like a very small number. So what would happen in this case? Again, there is no cross-talking, right? So the whole idea of attention was to somehow use embeddings from different words in individual embeddings. So the way that we do it, okay, so we said we'll learn some vectors of, for each of them, look at the similarities, we'll bring that as a probability, then we'll sum it up based on that probability. But what happens if you end up with very small probabilities of other words? Because each word is really important for itself. So the similarity between the query and the key for that word is probably high. In fact, this can be the case. In order to avoid that, we can do the following. We can apply the same self-attention multiple times. Let's say 8 times. But the output of each self-attention, let's say, is much smaller than the 512. Let's say it is 64. So I apply a self-attention, I get output vectors of length 64 for x1, x2, and x3. Maybe I will have another real initialization, apply self-attention with different parameters, everything, get another set of outputs, and I'll concatenate. So if I apply 8 self-attentions and the output length of each vector is 64, then the overall concatenated output will be 512, which is the intended length that I had in mind. So that is the idea of multi-head attention. Okay, so, all right, so I'll be a little bit fancy. Technology. All right. So I have x1, x2, x3. I apply the first self-attention, let's say with matrices W0Q, W0K, and W0V. My output will be 3 vectors. It's a design choice, but I designed the output to be vectors with length 64. And I can do it by designing the W matrices with appropriate dimensions, like 512 to 64. Now I'm going to have another, again, self-attention, W1Q, W2Q, K, and W2, W1, K, W1V. I jinxed. And the output will be another set of vectors, again, 1 for each token, 64, and I'll do it 8 times. Okay, so then I'm going to concatenate the vectors corresponding to each position. For x1, I have 8 vectors, each length 64. I concatenate them. Concatenate. So here I concatenate these 3 vectors. I will get a vector of length what? 8 times 64, which is 512. Same for the second token, same for the third token. So this is my output. Okay, you'll probably hate me, but in the design, they multiply with another matrix individually. So that really doesn't hurt because there's no cross-talking, but it adds flexibility. So that matrix is called the WO. And this will be the final embedding. This is Z3, Z2, Z1. This goes to what? Feed-forward network that we described. Feed. That is it. So that is basically it. That is the encoder side. To summarize, let's have everything in one picture. So we have X. These are X1, X2, X3. So you take your word embeddings at positional encoders, you get X's, right? Then you apply 8 self-attention encoders, 8 heads, WQ, WK, WV, let's say for the first one, the second one, 8-1. So you get Q0, K0 V0, Q1 K1 V1, Q7 K7 V7. You concatenate and you multiply with vector W0, and then you get your 3 embeddings that we call Z. This is Z1, Z2, Z3. So remember, the output of each encoder, there are 3 vectors. Here, the length is 64 because we have 3 inputs. You concatenate 8 of them, you get 8 times 64, 512, and then you add another linear projection, you get your final embeddings. Okay, so one last trick in the design is, okay, so what is the dimension of the input? 512 for X1. The encoded version of X1, Z1 has also 512. Let's just sum it up as our final output, like residual networks. That helps avoiding the diminishing gradients in the training. Similar idea. So that's the residual layer. So you have X plus Z. So you get these vectors, again, 512. And if you wish, you can do some row normalization, or it's called layer normalization, but that's not really important. It just makes each row, roughly speaking, 0 mean and unit variance. Believe it or not, that's the encoder side. So if you look at it from a little bit higher level, so we have self-attention. Hold on, don't go. X1, X2, X3. Then you have this residual layer. Basically, the output of the self-attention for each X1, X2, X3, there's Z1, Z2, Z3, same lengths. You add them up, and perhaps you normalize. That's it. You get 3 vectors. You apply your feed-forward net layer, as we discussed. Feed forward. If you wish, you can add and normalize again for this part. And that is it. Your output, there are 3 vectors with 512 length. Encoding, hopefully encoding the information not only in that particular token, but also in this context. And then you can repeat this block 8 times on top of each other, or as many times as you wish, 6 times, 10 times. That is the encoder of a transformer. That is, in fact, an encoder that is being used, or variations of it is being used in state-of-the-art models, ranging from ChatGPT to other models that probably you have heard. That is it. See, it's like taking tokens, embedding it into another space, but with an idea. As you can see, many of them are like somehow design choices, saying that how we can incorporate the information of the other inputs. Perhaps you can come up with like maybe alternative, better design for such a task. Next, I'm going to talk about the decoder side of a transformer. So as I mentioned, the decoder is going to be working in an autoregressive fashion. What that means is that suppose you decoded the first 2 or 3 tokens. you generated the first 2 or 3 words as your output. Then you assume that those words are your input and you generate the next word. That's the autoregressive way of generating the next token, the next word in the decoder side. So in other words, you have a decoder. Here's the block that you have. Imagine that you already generated these tokens. Obviously, you start with a start token. And let's say the next token that you already generated is the token corresponding to the word I. And then the goal is to generate the next token. In our case, if you remember, the example was I love UMD. Right? So we want to generate the word or the token love as the next decoded word. Okay, we can use basically the same architecture. You already have seen how attention is going to work. So what we are going to do, we are going to first embed these tokens using your favorite word embeddings, add positional encoding vector to each of them, like the one that we did for the encoder side. So these are very similar processes. And then apply a self-attention layer. Apply a residual connection like the one that we just discussed. Add, and you can add a normalization. And perhaps use the same or similar feed-forward neural network architecture. Add and normalize. All right. So if we do this, basically we are using an architecture very similar to the architecture that we had in the encoder side, right? So the output will be 2 vectors here because I have 2 inputs, one corresponding for the token start, the other one corresponding for the token I. And let's say the length of these are 512 to be consistent. Then to predict the next token, we are just going to solve a classification problem and get the probability of the next word. And what is the number of classes that we have? The number of classes that we have is basically the number of possible words or tokens that we have in our dictionary. So we have a very large dictionary. Let's say I have 10,000 candidate words. I'm just going to train a classifier using these input vectors to see which word has the highest probability as my next word, as my next token. That's it. So here I'm going to use a classifier. So these are the 2 inputs. To predict my next token over the entire dictionary that I have. So if you consider like 10,000 words, then you're saying that, okay, so what is the softmax probability of word 1? What is the softmax probability of word 2 to word 10,000? And you pick the one with the highest probability, you generate that one as your output. You decoded your next word or next token. Then for the next step, you add the word that you generated to your input. Then you have 3 inputs: start, I, and hopefully you generated love as your next token, because that's the correct translation. And then you generate the next token. You decode the next token. Hopefully that is UMD. You add that for the next step of the decoding to your input. Hopefully, the next token that you generate is end of sentence, which means your translation is complete. And that's it. That is the decoder side of the transform. Easy, right? Would this work? What I explained here, do you think if I use it in practice, it will work? I hear one no. Why not? Yes.
I think because sometimes it, like language, word one will, like in one language might come as word three in the next language.
Yeah, that's obviously true
Yes.
across different languages.
Yes, so this type of like doing it word by word, how can that work? Like, that's the part I'm confused.
So, but the decoder is in your target language. So the input to the decoder is the tokens that you are generating in your target language. So I think that shouldn't be a problem. Someone from the back, yes. You gotta speak really loudly. No. So the one with the bluish blues, yes. All right. So yeah, your friend is making a good point. It is less important. It is not what I had in mind, but I think that's a good point. What your friend is saying is that we can't use the same self-attention layer, right? Because the attention is about how each word is contributing to the other word's embedding. But here you're decoding one by one. So the future word or token that you are generating shouldn't really have influenced the first, the embedding of the first word. So we need to impose some constraint on the attention. That is really easy. Basically, what we are going to do is we are going to zero out the upper diagonal in the attention matrix. But that is not what I'm looking for. So one more, yes?
I think it depends on the what the classifier is actually doing. If it's using a 2D approach or a specific sampling approach or a, like beam search sort of thing, it really depends on.
I don't know what beam search is, right? I want something simpler.
3D that is basically
No. Too complicated.
Dictionary, then it could just be that for all input sentences, it could be choosing the same.
No. I know what you're talking about, but I'm looking for something really simple. What is wrong with this picture? One more. Context of what? There is no context of encoder. So what I'm decoding from? So where did these two words come from? Start and I, and what should I predict for my next word? If I'm just generating a sentence, the next token can be anything. I ate ice cream. So remember, the task is translation, right? So we did the whole part on the encoder just to encode the information of my input sentence and to somehow use it in the decoder, right? So that is the missing part. So we have the encoder here. X1, X2, X3. This is my encoder. Remember that the job of the encoder is to somehow massage these vectors representing each token so that it is useful for the downstream tasks. For example, here for the decoder. Okay, so what we had a bunch of encoders, encoder 1, then we stacked up with another encoder up until encoder, I believe 6. Okay. So the output of the encoder, there are 3 vectors corresponding to X1, X2, and X3. So how can I use the encoder information in my decoder. So do you have any ideas? How can I make them talk to each other? So we have already seen a process to make tokens talk to each other in the encoder side, right? Now I want somehow my encoder tokens or the encoded vectors from the encoder side to talk to the tokens in my decoder side. So what should I do? Yes.
You can use the matrix again, like query and vectors, and then just without multiplication or something like that.
Very good. So I need something like attention, right? Attention mechanism, right? Remember, in the attention for the encoder side, the idea was that, okay, so each token should, the embedding of it should be a function of other tokens. And that was the idea of the embedding. Perhaps we need some cross attention between the encoder tokens and the decoder tokens. Okay, and that's precisely what has been proposed. We add a layer called encoder-decoder attention. And obviously, we'll add residual connections and normalization as before. Cross attention. Okay, so in order to compute attention, we needed the keys, K matrix or projection, the values V, and also Q, the queries. We need K, Q, and values. Okay, so in this architecture, these two matrices, K and V, is going to come from the encoder side. And the last one is going to come from the decoder side. Because we need somehow the encoder and decoder to be coupled with one another. So I cannot have all of these three matrices come from the encoder or all of these three matrices come from the decoder. But with this, we are able to couple the two. There's a question. Yes?
There is no way we should scale V from one and from the other or some other combination.
Okay, so there are some intuitive reasons. I'm sure maybe in the design, a few choices it has been tried. But if you remember in the attention, if you think about like the attention matrix P, right? So how do we compute the elements of P? You take the query vector for a token, and then you multiply it with various k's, that various k1, k2, kn vectors to see what are the ones that are similar to that particular group. Right? So therefore, and we multiply whatever probabilities that we obtain, we multiply with the corresponding values. Right? So therefore, it makes sense to have k and v to come from one side and Q to come from the other side. But this is the design choice that has been made for the cross attention. All right, so this basically aligns the encoder and the decoder side, and learning is done through that. So usually in the visualizations, people, they put an arrow from the encoder to the cross attention layer in the decoder. But I'll finish the decoder side with one last note, the one that your friend mentioned, about the attention matrix that we use in the self-attention layer in the decoder. right, so since the decoding is done in an autoregressive fashion, so we cannot have a dependence between one word and the future words. So because the embedding of that word should depend on the words and tokens before that and itself. Right? So that is the architecture, that is the constraint that we want to impose on the attention. In other words, what we want is that if you look at the attention matrix, we want these elements to be 0. So we want these elements to all be 0. So how can we do that? Just force them to be 0. Right? That's called masking. Make them 0, just normalize to make sure that the rows are probabilities. The way that is being done, the similarity values are considered to be -infinity. So when it is passed through the softmax, it is automatically going to be mapped to 0. So this is called masking. Enforced by masking. Believe it or not, that is it for the transformer. So we have an encoder. You take your input tokens, input words. We have the vector representations of each of them, but they don't know about the context. You pass them through an attention layer. Now they talk to each other with certain probabilities that are being learned. You get the same number of vectors as the output of the attention, add and normalize, basically a residual connection. And then you push them to the feed forward individually, just to make the representation a little bit richer, add and normalize, add to the input, normalize to have balanced means and variances, and that's it. That's the output of one encoder. You can stack up various encoders. And the decoder side, you start with the start token. Again, you process with the same blocks. The only difference here is that you add a cross attention block to get the information from the encoder side. And the way that it works is you get the Q, you get the K and V matrix from the encoder side. You learn the Q from the decoder side, from the previous tokens. Add and normalize, feed forward, add and normalize. You get the output vectors, and then you solve a classification problem over the dictionary that you have, see which word or token has the highest probability as your next word, generate that. That's one step of the decoder. And then for the next step, add the generated word to your input, generate the next word, and keep going. That is it. That is basically the model that is used in almost all state-of-the-art language models, ChatGPT, other types of models. As you can see, the architecture is not very complex. All right, so